Hi, here's the fourth video in the Applied Math for Game Development series, and this is about how to code some of the maths that we've seen so far. So most languages worth their salt have maths libraries, which gives you access to a bunch of maths related codes. Rookie mistake there. So this library contains a bunch of math functions for you to use. C# is no different. It has something called a math class. And some of the functions I'm going to show you are ABS, AXP, POW, SQRT, and SIGN. ABS is short for absolute, and this is indicated in maths by putting bars around the value on the left and right hand side of it. But another way you can do it is you can do the square of a number and then do the square root of it, so you'll always end up with a positive number when you do that. So you can write it as bar A bar equals square root of A squared. But that's not too helpful in programming because it's quite inefficient to do that. You can use the ABS function, ABS function, which is the method signature looks like that. You'll get a double precision number as a result. That's why you see the word double here. And you can get that from a double number which you use an input parameter. This is also a static function, so you can use it anytime. EXP is short for exponential, but specifically in this case, the exponent of E, the Euler's number, not Euler's number. The guy's name is Leonhard Euler. I think he's Dutch, is he, or Belgian, something like that. So that's why it's pronounced that way. This is to do with logarithms. It's used in things like calculating interest, probabilities, certain physics equations, and so on. So exp double D, again, you give it a double precision number as an input, and it will give you e to the power of that number as a double precision answer. POW is short for power, and it's used to raise numbers to powers. So don't get that confused with EXP. Sometimes it's quicker to do it yourself. For example, instead of squaring things using POW, you could say x multiplied by itself, x star equals x. Or if you don't like that notation, you could say x equals x times x. That's quicker than doing x equals math.pow x comma 2. But it wouldn't be quicker if you had to do math.pow x comma 10, because you'd say x equals x times 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 x. I'm not even sure I got the right number of x's there, so easy to make a mistake as well. So that's how POW works. You give it two numbers. One is a number you're raising to an exponent, and the other is the exponent, and it'll give you a double precision answer. SQRT, short for square root, so we call it square root or sometimes squirt. So the square root is calculated, it's often done using repeated operations. For example, Newton's method. I think most CPUs have built-in routines to, what? That was weird. It has built-in routines that are quicker than using Newton's method, but it can be done that way. But repeated methods are pretty slow, relatively speaking. And if you can find an alternative way to code something without using a square root, then it may be more efficient to do so because it is slow. I mean, one square root is neither here nor there, but if you have a lot of them done every frame in a game, that can slow things down. So an alternative method would be better. And that's why there's something called the fast inverse square root. We'll come back to that another time because it's a nightmare. But anyway, the square root function, give it a double precision number, and it will tell you the square root of that number. Lastly, the sign function, pretty simple. It'll give you a +1 if the number you provided is positive, or a -1 if the number provided is negative. So because it's only a plus or -1, it returns an integer, even though the value you put in is a double precision. It might not sound too useful, but actually it can be pretty useful. All right, so how to do expressions and compose functions. So in maths, if you have a function, it looks like this, f of x or g of x. That's how we usually call them. And you can make a composite function by combining them. So you'd say f circle g of x, or you could say f of g of x, two different ways to combine them. In programming though, functions return values. So you can compose functions in an expression like this. You can work out the speed of something by getting the square root of x raised to the power 2 plus y to the power 2. That's obviously Pythagoras method, if you know that. But if you take the x value of a vector, square it, so the power of 2, add on y to the power of 2, then you get a number that goes into the parameter of the square root function. So this answer is composed of a composite of the square root and power functions. Because of, it's not quite BODMAS, but because of the order of operations, POW functions are evaluated first, that one, then the addition is done, then the square root is done. But you can do these numerical functions yourself. For example, the sine function, this is how it actually works. When you're given a number in a sine function, check if that number is greater than or equal to 0, and if it is, you return a +1, otherwise you return a -1. If you want to do your own version of the absolute function, take the number you're given. If it's less than 0, then you return the negative of it, because it is, if x is a negative in that case, so if you return a negative of that, it'll turn it into a positive. That's negation. But if it's already positive, just return it. So either way, you get a positive number. That's what absolute is. If you wanted to do an integer power, it's basically big pi notation. X to the power of n is big pi of x from k equals 1 up to n. It's a long form of writing it, I guess, in maths. But again, big pi just means a loop. So first we put in a line where if exponent is 0, return 1, because anything to the power of 0 is 1. But then we start by having the result equal to whatever x is. So whatever number you're raising to the power of, we start from that number. And then we keep multiplying by itself as many times as we're told to by the exponent. So this is only working for integers exponents, that's why that's there. So as long as the exponent is greater than 1, because if the exponent is exactly 1, then it's just x. But if the exponent is greater than 1, multiply the result, which was x, by itself again. So you've squared it, and then the exponent goes down. So now the exponent, if it's still greater than 1, that means you must be cubing it. So you multiply by x again, the exponent goes down. If it's still greater than 1, then it's to the power of 4, so you multiply again, and so on, until the exponent reaches 1. Then you've got your answer. Now, if you want to do square roots, you can do it as a repeated recurrence relation. There's the approximation of it there. It is an approximation because you can't keep on doing that infinitely. But however many digits of precision you want, you can get them. You can always get them if you just keep on doing that long enough. Here it is in code. So you want the square root of any number. We keep it a floating point for now. Start with that number halved. And we repeat it in this case 100 times, but you could change that to however many you want to get the level of precision you want. And so what we do is that recurrence relation 100 times. The next value we want is equal to the previous value plus the number we're getting the square root of divided by the previous value. And that's all over 2. 2d in decimal, that's what that d is for. So divide that all over 2. That's one recurrence relation. It repeats that 100 times, and the number will gradually get closer and closer to the actual square root until we're happy with the answer, and you return it. That's that sigma expression from before, just put in as a reminder to move us on to the next section. But sum of n from n equals 1 to 5, just put a for loop in. From 1 to 5, add on n. The reason that's there is to compare to big pi. So a factorial, n factorial. So that's big pi of k from k equals 1 to n. Again, that's a for loop. We do put in that extra line to deal with x equal to 0 especially. But otherwise, we start at n equals 1 and multiply by the next integer as we go on until that integer reaches x plus 1. And that's your answer. That's the way to do a factorial using a while loop, a for loop. It can also be done using recursion. Now, recursion is a special version of a function call. If you want to get a factorial of any number, then we check if the number you're getting a factorial of is 0. 0 is always a special case. And if we find 0, the factorial of it is 1. Any other number can be worked out by getting the factorial of the previous number, because that's how factorials work. You always multiply by the next number. So you can do it in reverse and work your way down. And so it's going to call up itself repeatedly. Let's say you want to get a factorial of 4. X is 4. 4 is not 0, so return 4 times the factorial of 3. 3 is not 0, so return 3 times the factorial of 2. 2 is not 0, get 2 times factorial of 1. 1's not 0, get 1 times factorial of 0. 0 is 0, it returns 1. So you get 1, loop back round, times 2, times 3, times 4, times 5, as it exits those get factorial functions that were called up. Pretty complicated, and that's not the way I would do it. But that's how recursion works. The function calls itself several times deep, and eventually it finds some return value, and then loops back around again to get back to where it started. I'd probably, unless you think you get the idea of that, I would probably avoid it and stick to the for loop version for now. All right, so a few more things to look at. How to manipulate fractions in code. So we talked about how to turn a terminating decimal into a fraction. Let's take an input decimal, and we want to represent that as a fraction by having a numerator and a denominator, two separate numbers, so that we can represent that fraction accurately no matter what it is. So we'll create a temporary numerator, and we're going to start that by making it the same as the input decimal number, whatever that was. Set the denominator to 1. So effectively we're saying, take the number you gave us and make it into a fraction, something over 1. Which is, you can always do. That's a fractional representation of any integer number. And then 7 times we're going to repeat this loop because there are 7 places in a IEEE floating point number. No point doing more than this. So again, you just repeat this for however much accuracy you want. In this case, we want 7 digits of accuracy. And as you go through those places, we check if the numerator mod 1 is equal to 0. So if you do a modulus, then it's dividing by that number. And if you're left with 0 remainder, then your temp numerator is 1. So, sorry, is not 1. So that means you've found the last digit. If you haven't found the last digit, then both the numerator and the denominator are multiplied by 10. So both sides of the fraction go up by a factor of 10. And you keep on doing that until you're left with a 0 on the right-hand side of the decimal place in the temporary numerator. Okay, so then you're left with the actual numerator. So let's just set the numerator to that. And your denominator has been going up as you go along. So you've found the numerator and denominator. And because they're output parameters, they will be returned to whatever called this function. What if you want to reduce the fraction? The code is starting to get a bit hairy here, but you can't divide by 0. So the first thing we'll do is check if your denominator is 0, and if it is, we'll throw an exception. That's just stopping you from accidentally dividing by 0. But assuming you're not trying to divide by 0, we find the greatest common multiple. So that's actually the hard part. We make these two integers, n1 and n2, we make them both absolute values of numerator and denominator, and then keep on repeating this loop where if the numerator is less than the denominator, then we swap the two operands together around. So we make a temporary int, set it to n1, make n1 equal to n2, and then n2 equal to the temporary one. So we've swapped n1 and n2. So what we can do then is we can guarantee that n1 is always going to be larger, because if it's smaller, we swap them. If it's not smaller, we don't swap them. So n1 is always going to be the larger, either numerator or denominator, but it's always the larger one. And if you get that larger number divided by the smaller number, but with a modulus so that you get the remainder, then that's you found a multiple. So you keep on doing that while n1 is not equal to 0, and that loop will exit when you've found the greatest common multiple. So n1 is the greatest, sorry, n2 will be the greatest common multiple. So you just divide both the numerator and denominator by that, and you've reduced your fraction. Okay, finally, we're going to look at complex number multiplication. Before I do this code, let's go back to Paint and try an actual example. Now remember, complex numbers can be drawn like so. You can put in the real number, 3 plus, and then an integer, sorry, not integer, an imaginary number, 3 plus 2i. There's a complex that represents effectively the vector 1, 2, 3 along, and 1, 2 up. So that 3 plus 2i represents a vector which looks a bit like that. And if you then multiply by another vector represented as a complex number. Let's say 2 plus 3i. And that's a bit like saying 2 along and 1, 2, 3 up. So both of these examples, you've got a little angle here and here. And if you multiply two complex numbers together, effectively what you're saying is take this angle and add on that angle there. But let me prove that. So 3 plus 2i times 2 plus 3i. What we do is we use a system called FOIL, which stands for first, outer, inner, last. Also called the claw. So you could take the 3 times the 3i, the 3 times the 2, 2i times the 2, and 2 times the 3i. You've got a kind of a claw shape there, reaching around the numbers. I prefer FOIL, but some people like the claw as a visual representation. But anyway, FOIL, first two terms, 3 times 2, 6. 3 times 2. Then the outer terms, the O. So the outer terms at the left and right hand side of the whole thing, 3 and 3i. 3 times 3i. And then the inner terms, 2i and 2. I'm going to run a space here, let's expand it. 2i times 2. And finally the last terms, 2i and 3i. 2i times 3i. Okay, 3 times 2 is 6. 3 times 3i is 9i. 2i times 2 is 4i. And 2i times 3i would be 6i squared. Now we can simplify that. 6 plus, there is 9i and 4i, add them together, you get 13i. 6i squared, well, I squared, what is I? Let's say 6 times something squared. What is I? Well, I is defined as the square root of minus 1. So if we've got a square root, which is being squared, those two will cancel out. So effectively, that's 6 times minus 1. So we've got 6 plus 13i plus 6 times negative 1, or negative 6 in other words. So 6 plus negative 6, they cancel out. We get 0 plus 13i. So if we go 0 along and 13 up the way, we've added on those two angles and ended up with a straight line going straight up. Maybe you can't tell from the way I've drawn this, but if you were to add that angle there on, here, that's what you get. So complex numbers multiplied together can represent a rotation. Now, anytime you see I squared, because I is the square root of minus 1, you will always get negative 1. So you can code it this way. If you've got some structure called complex, where you've got a real number component and an integer number component, let's take another example. 2 plus 6i times 3 plus 4i. You can multiply them together. So you take the two real parts and multiply them. You take the two imaginary parts and multiply them, but turn it into negative because it's the square root of negative 1. And then the imaginary part is 2 times 4i plus 6 times 3i. That's that part there, ai times br. So complex number multiplication is actually relatively simple in terms of code. It's two lines with two multiplications and add and subtract. Very quick for the computer to do compared to things like rotating using sine, cosine, and arctangent. But it does take a wee bit to get your head wrapped around. And I think that's a good place to leave it for now.